and the other is optical microscopy and its variants. Now, firstly, we'll start with polarization. Okay. Now, when we talk of polarization, let me first discuss when we draw a wave like this, what does it represent? Because see, if you think of transverse waves, like when if you throw a stone on a pond, you have these transverse waves, and this represents the movement of the particles. This is the direction of energy propagation, and this is the movement of particles, water particles, you can say. But light can travel through vacuum, so there are no particles, there is no medium. So what do this wave represents? Well, we know this wave that we draw, the sinusoidal wave for a monochromatic beam of light, is nothing but the locus of the tip of the electric vector. We know that light is an electromagnetic wave, so we have an electric field. Let's say the electric field is in the plane of this whiteboard and it's going in this direction. Okay, so this is the instantaneous locations of the electric field. And if the envelope of the tip of the electric field is the wave. So this is what is represented by when we write, let's say, ET, that is the instantaneous electric field, is the amplitude into cos omega t. So this is the amplitude. So this is E naught, and ET is the instantaneous electric field. So this is the electric field, and we also have attached to it the magnetic field, which is in the orthogonal direction. Okay, so we know that the electric field and the magnetic fields are in orthogonal directions. Okay, now when we talk of polarization of light, why I am mentioning light is we also know there is polarization. The term polarization is also used in a different sense. For example, dielectric polarization. So that is a different concept. We're talking of optical polarization. So if the electric field is restricted to one plane only, for example, the plane of this whiteboard, that is, the electric vectors are moving up and down, and the envelope of these electric vectors is a sinusoid of this form, then the electric vector is restricted to the plane of this board only, right? It is not moving in different planes. It is only moving up and down in the plane of this whiteboard. And we say, in this case, we say light is linearly polarized. Linearly polarized. Okay. Now, it is not essential that the electric field is always restricted to the plane of the board. It can be in various directions. If it is restricted to the plane of the board, so that the electric field moves in this manner, okay, then we will say light is linearly polarized, and we will give a symbol like this. It's a vertical line extending up and down, showing the extent of the electric field, the amplitudes in both the directions, positive and negative. And this is the representation for linearly polarized light. And specifically, this will say is vertical, or in abbreviation, vertical linear polarization, or LV, linear vertically polarized light. Okay. Now it can so happen that the electric field is moving not in the plane of this whiteboard, but normal to the plane of the whiteboard, like this. Okay. So the magnetic field and the electric field have interchanged. The magnetic field must be something like this. Now, if this is so, then the electric field is moving in this plane, which is normal to the plane of the board. Then we will draw something like this, and we'll say light is horizontally polarized. Okay, so this is linear horizontal polarization. It is not VLP, it is linear vertical polarization, and this is linear horizontal polarization. In fact, light can be linearly polarized in any arbitrary direction. Okay, so we can have if this is my x and the y coordinate, which is The laboratory coordinates are usually vertical, horizontal, and vertical, which are denoted by X and Y. You can have horizontally polarized light. You can have vertically polarized light. You can have light polarized at 45 degrees, which means the electric field is moving in a plane which makes a 45-degree angle to the plane of this whiteboard. Okay, it can be minus 145-degree polarization. It can have any, well, direction. The electric vector is moving in one plane, but that plane makes an angle with the, let's say, the reference horizontal plane. Okay, so this is linearly polarized light. Now, ordinary light is not linearly polarized. The light we see from incandescent lamps, from the sun, they have arbitrary polarization. Well, we are coming to that shortly. Now, it can so happen that during this oscillation, the electric field is changing planes. For example, if this is the direction of propagation, Z, it is directed in the plane of the board right now. At the next instant of time, it changes planes and goes here. Then it goes here, and then it is normal to the plane of this board. Then it is going in the opposite direction, and so on. So, what will be the locus of the electric vector? The locus of the electric vector, because the electric vector is no longer restricted to one plane, the locus will be, in general, an ellipse. And this ellipse may be because the electric vector may be rotating. You can think of a spiral. You can think of a spiral like this. So the spiral may be right-handed or left-handed. Okay. So the electric vector can be left-handed. This is the polarization ellipse. We call this the polarization ellipse. It can be left-handed or it can be right-handed also. Okay. So this is elliptically polarized light. This is also elliptically polarized light, but the two senses are different. Okay. And as it changes planes, if the amplitude or if the magnitude of the electric vector remains constant throughout, then obviously we will have circular polarization. Okay. And circular polarization can also be left-handed or it can be right-handed. Right. Now, what about unpolarized light? Well, in unpolarized light, just hold on. Page 2. How do I go to the other page? Well, in case of unpolarized light, we cannot define any such plane along which the electric vector is moving. It moves arbitrarily. So the electric vector is changing planes arbitrarily. At one instant it is here, at the next instant it is here. The amplitude will also, the magnitude of the electric vector changes randomly, and the planes also change randomly. Okay, so there is no proper representation for unpolarized light. For example, linearly polarized light is like this, which means it moves in a horizontal plane. It can be vertical, it can be in any plane, 45 degree, minus 45 degree, and so on. Okay, it can be elliptical, it can be circular, but for unpolarized light, what we can draw is a completely random pattern. The electric vector is moving about completely randomly. Okay, that is to say, if we know the location of the electric vector at this instant of time, we know that after, let's say, t by 4, that is, t is the time period for the electric vector to come back to this position, we know that after t by 4, it will come here if it is left-handed. Okay? We know after t by 2, the electric vector will come here. And we also know how its magnitude changes. It depends on the major and minor axis of the ellipse. Okay? The same with linearly polarized light. If we know at t is equal to 0, it is here, then at t is equal to t by 4, it will be at its extremity. Okay, at t is equal to t by 2, it will come here. So in case of polarized light, if you know the location of the electric vector at any instant of time, you will be able to predict the location of the electric vector at any other instant of time. Unlike unpolarized light, where the electric vector is moving randomly and it is impossible to predict its location at any other instant of time. Well, next we come to representation of polarized light. Well, if we have light polarized in any arbitrary direction, we can easily say this is x, this is y, and this is linearly polarized light, you say, we have said, and we can decompose those into two components. Okay, if the amplitude is a, then the x component is a cos theta and the y component is a sine theta. Now these two components are enough to define the state of polarization. Okay, we are talking of linearly polarized light for the time being. So we can represent these two components in form of vector a cos theta and a sine theta. So this is my, what are these? These are the x component and this is the y component. This vector is incidentally called the Jones vector. You will have find reference to Jones vectors when you are doing quantum optics proper. It's extensively used in quantum optics. So what does Jones vector represent? It's basically the x component and the y component of a linearly polarized light. Okay, so what will be the Jones vector for, let's say, horizontally polarized light? We know that now it is always, okay, just one more thing. Suppose we have a Jones vector of 3 and 6. What does it mean? It means that the x component is 3 and the y component is 6. Now, this represents a state of polarization. Okay? So we can very easily write it as 3 into 1, 2. Because we have to, usually we reduce to its lowest terms. Why? Because we are not interested in the amplitude of the light beam. We are interested only in the components. Right? So, now to expand this a little further, suppose you have these two vectors, the resultant is this. Now, if you multiply both by equal amounts, the resultant doesn't change. The resultant is always the same, okay? If you multiply both the component by equal amounts, the resultant doesn't change. That is to say, we will reduce the x component and y component to its lowest fraction. So, if we have, just a minute. Okay, so if we have linear horizontally polarized light, we can represent it by the Jones vector. We have the x component, we will normalize it to 1, and the y component is 0. So the Jones vector of horizontally polarized light or light polarized along the x direction is 1, 0. The Jones vector of light polarized vertically, similarly, because it has no x component, the x component is 0. Here the y component was 0, so the second element was 0. And here we will write it as 0, 1. Right? What about 45-degree polarized light? If we have 45-degree polarized light, something like this, then you see, say if this is 45-degree, then the x component and the y component both are 1 by root 2. So it's 1 by root 2 and 1 by root 2. So this is my Jones vector. And as I said, we can easily bring down to its lowest terms, which is 1, 1. 1 by root 2 is not important because it just indicates the amplitude of the light beam. 1, 1, this represents the state of polarization of the light beam. So whenever we say 1, 1, we see 1, 1, we know the Jones vector 1, 1 means that light is polarized at 45 degrees. Similarly, if you have minus 45 degrees, if light is polarized at minus 45 degrees, then we can write it as 1, minus 1, or we can write it as minus 1 1. Well, both of them represent 135-degree polarized light. Because why? Because firstly, we can take minus 1 as common from this and we'll get minus 1 1. And the physical explanation is you see the electric vector traverses on both sides of the center, right? If you consider this side, here the x component is negative, the y component is positive. On this side, the x component is positive and the y component is negative, but they are representing the same state of polarization. Therefore, if you just take out minus 1 from here, then you're left with 1 1. So 1 minus 1 and minus 1 1, they represent the same state of polarization. Okay, they are equivalent. Right. So this far we have discussed about linearly polarized light. Okay, what about circularly polarized light or elliptically polarized light? Now, elliptically polarized light is formed if there is a difference between the x component and the y component in terms of phase. When we have linearly polarized light and you're taking the components along two directions, okay, the x and y directions, the components are oscillating in phase. Remember, this vector, this electric vector is not fixed, right? Because it's the electric field of the light wave, which is oscillating at the frequency of light, which is about 10 to the power 14 times a second. So this is oscillating, right? Of course, in one direction and definitely in one plane. Just hold on for a minute. Okay. Now, what about elliptically polarized light? So, in case of linearly polarized light, the components definitely are in phase. In case of elliptically polarized light, the components, now we can write the components as A and B. So this is my Jones vector for, let's say, linearly polarized light, where the x component is A and the y component is B. And we can immediately say that the magnitude of the electric vector is A square plus B square root. Why? Because the x component is A, the y component is B, and the resultant, which represents the actual magnitude of the polarized light, is root of A square plus B square. So this is the uh, magnitude of the electric vector. And remember, in case of linearly polarized light, A and B are in phase. What about elliptically polarized light? When if there is a difference between the phases, so if we assume that A and B are real numbers, then we have a delta. So if there's a delta phase difference between A and B, then this becomes a Jones vector. And this represents elliptically polarized light. Okay. We also know that if you have two orthogonal vibrations, and if you combine them and if they have a phase difference of 90-degree, this leads to circularly polarized light. Now this is not essential, I mean, always for light. It's you can have a compound pendulum where you can have x and y oscillations separately, and if you can make a phase difference of 90 degrees between the x and y oscillations, which is to say, if the x oscillation starts from the equilibrium position at the center, the y oscillation starts from its extremity. So that is the 90-degree phase difference. Okay. Then you will see the bob at the end of the pendulum that is just rotating in a circular manner. In the same way, if you have an x component and the y component, and if they have a phase difference of 90-degree between them, which means when the x component starts from here, the y component is already at its extremity. Okay. Then the resultant will be circular polarization. Okay. And so when A and B are equal, let us put it 1 and 1, and E equal to delta equal to pi by 2, well, this is circular polarization. So circular polarization is just given by 1, and this is e to the power I pi by 2, This is equal to cos pi by 2 plus I sin pi by 2, which is simply I. Okay, so 1I is the Jones vector for circularly polarized light. Okay, well, this is, if this is left circular, then for right circular this will be 3 pi by 2, so the result will be 1 and minus I. So this represents left circular polarization and this represents right circular polarization. Okay, and well, it is not essential that you will have only left circular and right circular polarizations. You can have any arbitrary polarization, elliptical polarization, where we might have, say, 1, 2 e to the power I pi by 3. Well, what does it say? It says that the x component is 1, the y component is 2, and the two vibrations, they have a phase difference of pi by 3, let's say. Okay, and the result will be, in general, an elliptically polarized light. That is to say, the electric vector is now moving, the tip of the electric vector, the locus of the tip of the electric vector is now an ellipse. This is in fact the most general form of polarization. Okay, when either of these uh, major axis or minor axis goes to 0, this degenerates to linear polarization. And when the major axis, minor axis are equal, this is circular polarization, right? So for circular polarization, the two conditions are the x component and the y component must be equal, and the phase difference between the x component and the y component must be equal to pi by 2. Okay, so now we know how to represent. We first of all, what we have discussed how polarized light differs from unpolarized light. Okay, in polarized light, if we know the location of the electric vector at one instant of time, we can predict the location of the electric vector at some other instant of time, which is impossible in case of, well, unpolarized light. Secondly, we know that linearly polarized light or polarized light can be represented in case of in the form of a Jones vector. This is the x component, this is the y component. If these two are real quantities, then it only represents linearly polarized light. If either of them is complex, if you have a complex term like here, then it in general represents elliptically polarized light. If A and B are equal and delta equal to pi by 2 or uh, well 3 pi by 2, then this represents, well, linear circular polarization, left circular polarization or right circular polarization. Well, from here now we can look into the analysis a little further. So this analysis is called Jones calculus, but there is no calculus involved. Okay, so we know, let's say we have a component, a polarization component, and the input is, let's say, AB. Well, this polarization component, whatever it is, this changes the polarization to A prime, B prime. Okay, it is not essential that A prime, B prime are real. You can have linear polarization incident on a polarizing device. The output can be circular or elliptical polarization. Okay, but if you want to write an equation relating AB and A prime, B prime, what we need to write is A prime, B prime, this vector, the output Jones vector, must be multiplied with something with AB, and the input Jones vector must be involved to get the output Jones vector. And this must be a 2 by 2 matrix. So let us write it as M11, M12, M21, and M22. This matrix is called the Jones matrix. So the Jones matrix What does it represent? It doesn't represent either the state of input polarization or the state of output polarization. It represents the device. So the Jones matrix is characteristic of the device, of the polarization device, right? So this is the importance of the Jones matrix. Now let us say we have another polarizing device here. Then the output becomes, let's say, A double prime and B double prime. Okay. Then again we can write A double prime, B double prime. This is equal to, let's say, this is P1, this is P2. So this Jones matrix, let us write it as M1. So again, we have to multiply this with the M2, which is the Jones matrix for the second polarizer, and write it as, this will write it as A prime, B prime. A prime, B prime was the input to P2, which has a Jones matrix of M2, right? But then we see A prime, B prime is also equal to M1 into AB. So we can write M2, M1 into AB from here, because this is equal to M1 into AB. So in place of A prime, B prime, we just replace this. So you see, if you have n number of elements, okay, P3, P4, right up to n, then we have the general equation that after the nth element, so an, bn, which is the state of polarization, that is the Jones matrix after the nth element. So you have a series of polarizing elements. Then we can simply write this as mn, mn minus 1, right up to m3, m2, m1, ab. আমি এটা ক্লাস একটু পরে ফোন করুন, হ্যাঁ, 5টার পরে ফোন করুন। ওকে, so this is the uniqueness of this Jones formalism, that you simply need to know the Jones matrices of these polarizers to find the output, right? So the next, what remains is to find out the Jones matrices, to evaluate the Jones matrices. So once we know the Jones matrices, we can easily find out we can easily analyze the polarization states after, well, if we know the input, we can easily find out the input output if we know the Jones matrix of a polarizing device. Okay, so now let us come to Jones matrices. So what are Jones matrices? We have seen that Jones matrix is a 2 by 2 vector, 2 by 2 matrix. Okay, and you have to, well, in a 2 by 2 matrix, we have to find out the elements of the matrix. Let us start with a polarizing device. Now we know what are the polarizing devices we generally encounter. Well, polarizer. Then we have quarter wave plate. And we have a half wave plate. Since you will be taking up quantum optics, this is very important to understand the working of polarizer, quarter wave plate, and half wave plate. Okay, first of all, a polarizer. When we say this is a polarizer, what we mean is, let's say this is a polarizer. Let's say this is a polarizer whose uh, well, transmission axis is along, let's say, this direction. So this is the transmission axis. So if this is the transmission axis, it means that if you have unpolarized light, now what is unpolarized light? Unpolarized light means light is oscillating in all possible directions. Okay. If you have unpolarized incident on the polarizer, the resultant electric field will, what will pass through this polarizer is simply along the transmission axis. So the output will simply be like this. If the polarizer orientation is vertical, let's say the polarizer transmission axis is vertical, then if you have unpolarized light here, unpolarized light is also represented by this kind of a figure where you have electric vectors in all possible directions, in all possible amplitudes, sorry, magnitudes, then the output will be vertical. Okay. So a polarizer selects the oscillation of the electric field in one direction. And what is that direction? That direction is denoted by the transmission axis. Why does it happen? Well, a little bit of physics. So these polarizers, well, we have crystal polarizers, but we also have these thin film polarizers, which are mostly used in photography and for lab experiments, low power laser lab experiments. These polarizers are basically long chain molecules. Okay, it's basically polyvinyl alcohol. So it's a polymer with long chain molecules, but the molecules can vibrate in this direction. Okay, only it cannot vibrate in this direction. So what happens if you have unpolarized light? And also remember that the frequency of vibration, the resonant frequency matches with the frequency of light, which means all vibrations in the direction of these long chain molecules where the material can vibrate, where the long chains can vibrate, they are being absorbed. So all, for example, if you at a certain instant of time, if this is my electric field, then you can think of this as two components, the x and the y component, at a certain instant of time. Okay. The y component sets up a resonant oscillation here. And we know that what happens during resonance is that energy is being completely absorbed. And that is why we know that troops are not allowed to march on a bridge. Okay, they are asked to disperse while passing through a bridge. So what happens is, in the direction of the long chain molecules where the resonant frequency applies, the y vibration is completely absorbed and the x vibration passes through. The x vibration is not absorbed because the long chain molecules cannot vibrate in the direction normal to the direction of the long chains, which means that the transmission axis is along this direction. So the direction of the long chain molecules is normal to the direction of the transmission axis. Okay. So this is a polarizer. Let us also briefly, we'll discuss this a little later, but let us briefly talk about, well, wave plates, half quarter wave plates, half wave plates. In general, these are called retarders. Now, what are retarders? You see, in an isotropic medium, if you have a point source here and if you allow light to propagate, suppose you have a point source which you can control, and at t is equal to 0 you switch on the point source. Well, at t is equal to, let's say, small t, what happens is light has propagated, let's say, up to this distance. Now, because this is an isotropic medium, the velocity of light in all directions are identical. And because the velocity of light in all directions are identical, the wave front, the energy have spread out to a sphere. Okay, the energy that started from this point after time t, they have spread out to a sphere of radius c into t. Right? Velocity of light is c. And we can say that this is my new wave front. Well, what happens in a birefringent medium? In a birefringent medium, there are two directions. Okay, one is the fast axis, the other is called the slow axis. Now, briefly, why this happens is we have to know how light travels through a medium. When light travels through vacuum, well, there is nothing to interact with. But when light travels through a medium, okay, for example, air, glass, water, what happens is the medium consists of positive, well, these are, well, these are, it's ions. Basically, you have, sorry, atoms. So you have the nucleus and the electron cloud. Okay. Now, suddenly, if you have an electric field, let's say it is polarized light, light is polarized in this direction, which means electric field is moving in this direction. So what happens? The electron cloud will be drawn like this when the electric field is upwards, and it will be drawn like this when the electric field is downwards. And this causes a charge separation. So in case of a perfectly unpolarized atom, the positive and the negative charges are concentrated at the center. But what happens if the electron cloud is distorted? Then you have the positive charge here and the negative charge here. Some it is displaced. So this constitutes an electron dipole. And this is not fixed because the electric vector is oscillating constantly. So this will go down and up, and the electron cloud is being displaced continuously. So this will constitute an electron dipole. And as the electron dipole vibrates, it will radiate energy, right? And we know that, well, maximum energy will be radiated in this direction according to the principle of the antenna, and so on. Now, we can, although this takes a little time. So if you have more number of, let's say, atoms in one direction and less number of atoms in the other direction, then obviously we can say that this will be the faster axis because there are less number of atoms to interact with. And this will be the slower axis because there are more number of atoms, and each of these absorption and re-emission. So what happens is the atom absorbs energy and then re-emits energy. So this absorption and re-emission of energy takes a little time. Okay, therefore light is slowed down. So more number of atoms you have in one direction, we can say light is slowed down more compared to where the number of atoms are less. The atom density along a certain direction is less, means light will travel faster. This is a general rule. There are some exceptions, but we're not going into that. So what happens in an isotropic medium, the arrangement of atoms are completely random. So as if you're standing in a crowd. So if you're standing in a crowd, in whichever direction you look, okay, the number of head count will be the same. But if you are in a very regular, let's say, pattern like this, which is in a crystal, so the atoms are sitting at lattice points in a crystal, then you see this direction and this direction, well, the separation between the lattice points may not be equal. Okay, in this direction it will be different. So the different directions will give you different spacing between the atoms. Therefore, the velocity of light changes as you change direction. So we are talking of retarders. We are talking basically of uniaxial crystals. Uniaxial crystals. Is the whiteboard and my voice clear to you? Any feedback?
Yes, sir. Your whiteboard is clearly visible and your voice is audible.
Thank you. Okay. So in case of uniaxial crystals, what happens is you have, just a minute. Yeah. In case of uniaxial crystals, we have a fast axis and a slow axis. So if you have a, let's say this is my uniaxial crystal in form of a retarder, it can be a half wave plate or a quarter wave plate or whatever it is. Now this has some thickness, right? Let's say the thickness is T. And This is my slow axis, this is the fast axis. So this is the slow axis, this is the fast axis. Well, I cannot possibly go much into birefringent materials, but this is in a nutshell what you need to know. So when light is, suppose linearly polarized light is incident on this retarder. So this is my state of polarization of the linearly polarized light. It is supposed to be a straight line. Then you have the x component and the y component. So light immediately breaks up into the x component and the y component, and these components will now travel with different velocities. Okay, because the refractive index, if the refractive index along the slow direction is ns and the refractive index along the fast direction is nf, n sorry, nf, and we know that ns is not equal to nf because this is not an isotropic medium. The velocity of light is different in different directions, and these are the two principal directions along which the velocity of light varies maximally. It is fastest along the y-axis, let's say, and it is slowest along the x-axis. So if that is so, then these components will now travel through the crystal at different velocities. Okay, the x component will see a refractive index of ns, assuming that the slow axis is along the x direction, and now it has to travel a distance of t. Let's say this is the thickness of the crystal. So if it has to travel a distance of t, then ns into t is the optical path. Optical path is refractive index into the actual path. This denotes the actual path in air. That is to say, if light passes through a medium of, let's say, n with a thickness t, then the optical path is n into t, which is to say that if it were to travel in air, it would have traveled a distance of nt in the same time as it traveled through the material. Okay, so ns into t is the optical path, and nf into t is the optical. This is the optical path along the slow axis, and nf into t is the optical path along the fast axis. So when it comes out of the crystal, they have a optical path difference. What is the optical path difference? The optical path difference is, of course, ns minus nf into t, because ns must be greater than nf. If the velocity of light is slow, then the refractive index must be greater. Okay, which is equal to delta n into t, and this delta n is what is known as birefringence. So the difference of refractive index along the two principal directions, this is called birefringence. What are the principal directions? The principal directions are the directions along which the refractive index varies maximally. Okay. Now, if this is my optical path difference, then what is the phase difference? We know that optical path difference of lambda, if this is lambda, the optical path difference of lambda is equivalent to a phase difference of 2 pi, right? One full wave period. In terms of phase, it's 0 to 2 pi. So lambda optical path difference corresponds to 2 pi phase difference. Therefore, x optical path difference corresponds to 2 pi by lambda into x phase difference. Therefore, delta n into t optical path difference corresponds to a phase difference, which is given by 2 pi by lambda into delta n into t. So this is the phase difference. Now, if this phase difference is pi, then we say it's a half wave plate. If this phase difference is pi by 2, we say it's a quarter wave plate. Why it's a quarter wave plate? Because in terms of optical path difference, in terms of optical path difference, this is lambda by 4. Okay. In terms of phase difference, it's pi by 2. Why it's a half wave split? Because in terms of optical path difference, this is lambda by 2, which is equivalent to a phase difference of pi. Therefore, it's a half wave split. Okay. Now, therefore, let us consider a general, well, optical polarizing element. It can be a retarder, any retarder. It can be, let's say, a polarizer. When we consider a polarizer, we will assume that the transmission along the y-axis is 0, right? And we intentionally have aligned this device such that the fast axis is here and the slow axis is here. Now, when we talk of a polarizer, there is no fast and slow axis. The slow axis is 0 and there is only one axis, okay, along which light is transmitted. So, let us assume and remember that retarders do not absorb light. Retarders are, they do not absorb light. Retarders simply introduce a phase difference between the two components passing along the x and the y axis. শুক্লা আমি একটা মিটিং এ আছি একটু পরে ফোন করি ওকে সো okay, where were we? Just hold on for a minute. Whiteboard has stopped. Yeah. So the amplitude here, if you write it as 1, the amplitude is also 1. But then a phase has been introduced between the two. So let us say when light comes out from here, the phase is e to the power I delta 1 from here, and it is e to the power I delta 2. And let's say this is the transmission along the y-axis and this is the transmission along the x-axis. So basically, a polarizing device can be thought of, uh, a polarizing device like a retarder can be thought of as two orthogonal directions along which you have an amplitude or phase transmission which are different. If it's a polarizer, then the, well, transmission along the y direction we'll consider to be 0 if the transmission axis is along the x direction, right? Therefore, let us say we have this kind of a device, okay, a general polarizing device where the input is AB and the output is A prime B prime. Well, then you have A prime B prime is equal to some Jones vector into AB. Now we know that the polarization of uh, these A and B are along the x and the y axis. We know this. So A component falls on the x axis and the B component falls on the y axis. So what passes out from the x axis is simply Tx into A because Tx is the transmittance along the x axis. And what passes out from the y axis is B into Ty. We know this. So this we know is equal to A into Tx and B into Ty. So we already know the result of this. And therefore, if we take this equation, then this should be Tx 0, 0, Ty. So we have A prime is equal to Tx into A and B prime is equal to Ty into B, right? If it's a simple polarizer, we'll write CTY is 0. So in case of a polarizer, the Jones matrix is 1, 0, 0, 0. When? When the transmission axis is along the x direction. Okay. Well, right. So we have Tx 0, 0, Ty. And this tells me that the Jones vector for a polarizer whose transmission axis is along the x direction is 1, 0, 0, 0. What about if it's a, let's say, quarter wave plate? Let's say a half wave plate. Let's start from a half wave plate. So what if it's a half wave plate? If it's a half wave plate, then the phase difference between this, well, there's the amplitude difference, okay? So this is e to the power, we can write this as e to the power I pi by 2, 0, 0, e to the power minus I pi by 2, okay? Which is equivalent to 1, 0, 0, e to the power minus I pi. So a phase difference, you have a phase difference of pi because we have said for a half wave plate, it's lambda by 2 path difference, which corresponds to a phase difference of pi. That is to say, you have a phase difference of pi between the x and the y components, right? Remember, AB, A prime, B prime is equal to this into AB. So then the output Tx into A becomes the x component and Ty into B becomes the y component. Okay. And there is a phase difference of pi between the x and the y components. So you have a phase difference of pi between the x and the y components in either of these, but we will generally consider this because this is more symmetric. In either of these cases, you have a difference of pi between the x and the y components. Okay. Where were we? See, I'm still getting used to this whiteboard. This is a new whiteboard I just downloaded, so bear with me. Okay, now, so you have Tx 0, 0, Ty. Now, what about a quarter wave plate? If it's a quarter wave plate, then this is either 1, 0, 0, e to the power minus I into pi by 2. Why do you write minus here? Because the y-axis is lagging. It's a slow axis. Okay. It's minus I pi by 2. Or we can write, this is equivalent to, if you take out e to the power minus I pi by 2, then we can write it as e to the power I pi by 2, 0, 0, e to the power minus I pi by 2. As we have said that this part is common to both the components, so you can neglect this. Okay, so this represents e to the power I pi by 2, 0, 0, e to the power minus I pi by 2. This represents, well, the Jones matrix for a retarder, for a, in this case, a quarter wave plate. Now, in whatever we have done till now, we have assumed that if it's a polarizer, then the transmission axis is along this direction. If it's a retarder, then this is the fast axis, well, the slow axis is here. And this will be said in normal orientation. normal orientation. So in this case, the the polarizing device is in normal orientation. But it is not essential that the polarizing device will always be in normal orientation. It can change orientations. For example, for a polarizer, the fast axis may be here. Sorry, in case of polarizer, we have no fast axis. The transmission axis may be here. Or in case of a retard, the fast axis may be here, the slow axis may be here. Okay? So there are ways to find out the retardation. In case of such, we have to take the rotation of coordinates and all that, but I don't think we have time for that because we have another chapter to cover. That's microscopy. Okay, but just to say that, well, how do we do this is, uh, it's simply rotation of coordinates. And if you have rotation of coordinates, for example, you rotate this coordinate by angle theta. Okay, and the Jones matrix of the polarizer comes out to be cos squared theta, cos theta, sin theta, cos theta, sin theta, sin squared theta. This becomes the Jones matrix of the polarizer. Now, if theta equal to 0, then this is my normal orientation of a polarizer. So for normal orientation, you see we have 1, 0, 0, 0 for theta equal to 0. This is the normal orientation. Okay. Similarly, we can have the orientation of a polarizer. We can find the Jones matrix of a polarizer for any orientation. And also, similarly, you can have the Jones matrix for a quarter wave or half wave plate. What we know is 1, 0, 0, 0. This is the Jones matrix for P 0 degrees, the polarizer oriented at 0 degrees. We also know if it's a quarter wave plate in normal orientation, let's say phi denotes the fast axis orientation is 0 degrees, then this will be e to the power minus, well, for a quarter wave plate, the phase difference is pi by 2, right? I'm sorry about this. This should be pi by 4 because you have taken pi by 2 here. So e to the power I pi by 4, 0, sorry, this is plus, this is 0, e to the power minus I pi by 4. So that the phase difference between the x component and the y component remains as pi by 2. And we also know the half wave plate, which is at normal orientation, which is equal to e to the power I pi by 2, 0, 0 to the power minus I pi by 2. Okay. But then we know that you can easily find out the Jones matrix for any arbitrary orientation of a polarizer. Okay. I think you can find it in this. There's a book called Polarization by Colette. Okay. I'm not sure of the spelling. It may be TTE, maybe L, I'm not sure. But this is a book where you can have all the derivations, how you do it. Similarly, you can have uh, the Jones matrix at arbitrary orientation for quarter wave plates and half wave plates, and we can use this to find out the output Jones vector, that is the state of the output beam for any arbitrary orientation of these polarizers. Well, let us do some example. For example, let's say we have a polarizer oriented at, the first polarizer has its transmission axis at 0 degrees. The second polarizer has its transmission axis at 90 degrees. What will come out? Now, it is easy to see that no light will come out. Why no light will come out? Because Well, the transmission axis here is 0 degrees, so we have unpolarized light here. We have unpolarized light coming in this direction. It's going in all directions. It's going in all directions. Okay, but here you have only this polarization. Now, the polarization along the x-axis, which is normal to this whiteboard, cannot pass through a polarizer whose transmission axis is at y direction. Okay, so no light will come out. Now, if we try to analyze this using Jones vector, what will we do? The input is, let's say, AB. It's any, let's say, it's any polarized light. Okay, it can be unpolarized light also, but we have no representation for unpolarized light. So let's say we have a polarized light, and what we have seen, if this is M1, this is M2, then we have seen that we have to pre-multiply this by M1 and then pre-multiply this by M2 and so on. Now what is M1? Well, M1 we know is 1, 0, 0, 0. And what is M2? M2 we know is 0, 0, 0, 1. Okay. If you multiply this with AB, if you carry out this matrix multiplication, you are left with 0, 0. That is, the x component will be 0, the y component will be 0. So now no light will pass through. So in this way, we can very easily calculate the output using this Jones matrix method, and this is widely used in quantum optics. Okay. Just to elaborate a little bit on these retarders, quarter wave plates and half wave plates. Well, let us first consider half wave plate. Now, what does a half wave plate do? We have seen that a half wave plate introduces a phase difference of pi, an optical path difference of lambda by 2, that is a phase difference of pi between the x and the y components, between two orthogonal components of a light beam. So let us imagine that we have a half wave plate, let us say in normal orientation. Let us say in normal orientation we have a half wave plate, and let us say this is the fast axis, it's the slow axis, and an input light beam is incident on the half wave plate at an angle of 45 degrees, let's say. So the x component and the y components are identical. So this is the x component, this is the y component. Well, they are identical. And what happens after they pass out? So the x component and the y component immediately after entering the half wave plate is 1 by root 2, 1 by root 2. They haven't traveled through the half wave plate as such. It's just entered the half wave plate. Now when they finally come out of the half wave plate, what happens is, so 1 by root 2 we can bring out. This is 1, 1. When they finally come out of the half wave plate, the y component lags by an amount of pi because it's a half wave plate. So you can write it as minus I pi. Well, what is e to the power minus I pi? Well, cos of pi minus I sine of pi, which is minus 1. Okay, this goes to 0, this is minus 1. So we are left with 1 minus 1. So what have happened? See, your input was light polarized at 45 degrees. X component was 1, y component was 1. The output is 1 minus 1. The x component is 1, but the y component is minus 1. So it has rotated by 90 degrees, right? Now this is true for any arbitrary linear polarization. So a half wave plate is used to rotate the state of polarization of a light beam. In general, if the fast axis of the half wave plate makes an angle of theta degrees, in this case theta is 45 degrees. So if the fast axis of the half wave plate makes an angle of theta degrees, to the linear state of polarization of the input beam, then the linear state of polarization of the input beam rotates by 2 theta, actually minus 2 theta. So now you see what happens is, this is the fast axis, this is the state of polarization of the input beam. This was 45 degrees in this direction, and the output has come here. It has rotated by 2 theta, by 90 degrees. Okay, so a half wave plate, if you allow light, linearly polarized light to fall on a half wave plate, you will never get elliptically polarized light or circularly polarized light. You will always get linearly polarized light, but it will be rotated. One more thing before we go on to quarter wave plate is that for any retarders, these are the two principal directions. Now, if you allow light to fall on these plates with the polarization either along the slow axis or the fast axis, then what will happen? The same polarization will pass through. Nothing will happen because you have no component on the other axis. So, if the input state of polarization is parallel to either the slow axis or the fast axis, then well, the same state of polarization will come out as the output, because only when you have two components, a phase difference between the two components can arise. Otherwise, no. Right. Well, now let us come to the quarter wave plate. Okay. So, in case of a quarter wave plate, well, the phase difference between the two components is always pi by 2. Okay, it's pi by 2. So the output, if your input is AB, if your input is AB, your output is always A B e to the power I pi by 2. Now, incidentally, if A equal to 1 and B equal to 1, which means 45-degree polarized light. So if you have 45-degree polarized light, okay, then this becomes 1 e to the power I pi by 2, which is 1I, right? So you have circularly polarized light. So a quarter wave, and if it is well, minus pi by 2, then it is well, if this is left circular polarization, then 1 minus I will be right circular polarization. That is to say that a quarter wave plate can change linearly polarized light to circularly polarized light if your state of linear vibration, the well, the linear vibration state makes an angle of 45 degree with the either the slow axis or the fast axis. Right. And for any other orientation, for example, if this makes an angle of 30 degrees or whatever, if this angle is not 45 degrees, then in general, you have elliptically polarized light. So a quarter wave plate is used to generate, in general, elliptically polarized light from linearly polarized light. Okay. And specifically, if it is 45 degrees, then you have circularly polarized light. Okay, if it is if the incident polarization is along this direction, making an angle of 135 degrees, okay, then you have, well, right circular polarization. Okay, so you see, we have only touched the iceberg of polarization optics, the tip of the iceberg. There's a lot and lot more, but I think this will suffice. If you need to know anything else, you can just consult. This is just to introduce you to Jones matrix and polarization optics, and the rest I think you can develop on your own because of my time limitations and all that. Okay, so we have seen what polarization is, what how do you differentiate linear state of polarization from circular and elliptical, and how to differentiate polarized light from unpolarized light. Well, how to analyze polarized light, it's a textbook material, you can go through and this study. And the Jones matrix formulation, which you would need in quantum well, optics, and the Jones matrices to analyze the state of the output beam when light passes through a series of polarizing elements. So the you can, what you have seen is, if this is my Jones vector, let's say, if this is my Jones vector, if let's say AB, then it passes through a series of polarizing elements. So you have M1, M2, and so on, right up to Mn. So all these matrices can be multiplied together to give you one single 2 by 2 matrix. And this one single 2 by 2 matrix will represent the series, the chain of polarizing elements you have. So this is the advantage of Jones matrix formalism. Well, I think there is no scope for questions, or we can do that later. Now, the next topic is it's microscopy, microscope, the optical microscope. Okay, so I'm going to discuss the optics of optical microscopes and eyepieces, etc., etc. So let me first draw uh, the simple microscope, and from that we will derive a lot of things, and you will have insight to what a microscope is and how it works, and uh, let me see how much I can cover. Of course, microscope is a very thriving topic, and you have a lot of microscope systems available these days. Okay, we have these stared confocal microscopy, a lot of things are available, but let me see what can be done. Okay, so if I want to draw a basic microscope, well, let's say this is my optical axis, and we have a lens here. Let's say an object here. This is my object, a microscopic object. And this is the microscope objective. So the lens which faces the object is called an objective. So this is my objective. So the lens which faces the object is called an objective. In a microscope, it's a microscope objective. In a telescope, it's a telescope objective. In a binocular, it's a binocular objective. So whichever lens faces the object is called the objective. Okay. In case of a microscope, it has a short focal length. It has a very short focal length. And we know that from imaging, we can, well, our school ray diagrams, we see that from the tip of the object, this is my object. Let's say it's a microscopic object which cannot be visualized by the human eyes. We try to visualize using a microscope. So we know from the tip of the object there are n number of rays, infinite number of rays there that are going out. We'll take two rays, the path of which we know. One of them will be a ray parallel to the axis, because we know that it would pass through the focal plane. The other ray we will take to the passing to the center of the lens, because we also know its path, it will pass undeviated. Okay, now these two rays will meet somewhere. Well, they're not meeting, I'm trying to make them meet. Okay, so this here, the tip of the object is recreated. Okay, so this is my image of the object after the objective lens. This is called the intermediate image. And then this drawing is pathetically out of scale. Here you have a eyepiece lens. The eyepiece lens is much larger than the objective lens. It is something like this. Let's say this is a lens. Now, a lens is usually drawn like this, but we will just neglect these parts. We'll draw it like this. Okay, because it's a thin lens, it should be a line. Now, what happens here? Well, the eyepiece is so placed when the microscope is in focus, the eyepiece is so placed that this is the focal length of the eyepiece. Okay, this was the focal length of the objective, and this is the focal length of the eyepiece. So the in focus, when the microscope is in focus, the intermediate image must be at the focal plane of the eyepiece. Now, what happens if this is so? Well, after the intermediate lens, after the eyepiece lens, so this is the eyepiece lens. Well, obviously, what will happen is the rays that come out of this will be parallel. Okay, why parallel? Because they are coming from the focus. So if we have a lens and if we have a point at the focus, then we know we'll get a parallel beam of light. If the focus on the focal plane, if you have a point here, then also we'll get a parallel beam of light, but in which direction? The direction is this. You have to draw the chief ray that passes to the center of the lens, and then all the rays will follow this chief ray and be parallel to them. So the light will go in this direction. So you have a parallel beam going in this direction. Now, eventually, this will cut the optic axis, which is this, and you put your eye here. We are putting your eye here, and the lens of the eye is receiving a parallel beam of light, and it is forming an image on the retina. Okay, and you will see the image at infinity. Ideal at infinity, but if this separation is a phi, right? So this is the geometry, the ray diagram of a standard microscope. But this is only the beginning. Now, let us say the object distance is u and the image distance, which is for the objective, the image distance is this, only this. The image distance is v, right? Then for the objective lens with a focal length of a4, we can write 1 by u plus 1 by v is equal to 1 by fo, right? A simple lens equation. So that is to say, v by u, now you multiply throughout by v. Now v by u is the magnification, and this is the magnification for the objective. Therefore, we write MO. So MO plus 1 is equal to v by f naught. So MO is equal to v minus f naught by f naught. Let us write this parameter t, t by f naught. Now, what is t? T is v minus fo. So, what is v? Well, v was this distance. Okay, you can see here. And what is f naught? F naught is here. So, what is t? T is this distance from here to here. This is t. T represents something called the tube length. Okay, T represents the tube length. In simple terms, a microscope is a monocular microscope. Of course, these days we have binocular microscopes where the ray from the object passing through the objective is now diverted into two eyepieces so that you have comfortable vision with your both the eyes. But actually, a simple microscope is just a tube like this with a length of t where the objective is screwed here. This is the objective. Well, this is the objective lens. It's a combination of lenses we have here. So if this is the principal plane of the objective lens, and this is the end point of the barrel, end point of the tube, then this distance is u. This is this. Sorry, this distance is fo. And on the other side, you put the eyepiece. The eyepiece is something like this. Okay, this is the eyepiece lens here, and this distance is fe. You put your eye here. Okay, so you can see t is on either side of t. What do you have? On one side you have the focal length of the objective, on the other side you have the focal length of the eyepiece, right? By international standards, t is taken to be 160 millimeters. This is international standard for the tube length of a conventional microscope. We are talking of a conventional microscope. Of course, microscopes have undergone tremendous transformation, tremendous advancements. So, the magnification of the objective MX, MOX, let's say, is given by 160 by FO. That is to say, if you have worked with microscopes in your biology lab or whatever, we know that usually microscopes come with 4x, 5x, let's write 5x, 10x, 20x, 40x, maybe sometimes 60x, and 100x magnification. Well, with 100x, it's an oil immersion. We'll come to that in a short while. So 5x means MO equal to 5. Okay. So when MO equal to 5, we can see from very easily see from here that FO is equal to 160 by MO. So when MO equal to 5, this is FO equal to 32 millimeters. This is 160 millimeters. Remember, the unit is millimeters. Therefore, 160 by 5 is 32 millimeters. So we know that a 5x objective has a focal length of 32 millimeters. Similarly, a 10x objective will have a focal length of FO is equal to how much? 16 millimeters. Well, a 20x objective, similarly, you can calculate will be 8 millimeters. 100x objective will have a focal length of 1.6 mm. It's a very, very short focal length. Okay. Now, whenever we view with the eye, of course, these days what you have is you simply put a CCD here. You put a CCD here. The CCD itself has some electronic magnification because of the size of the CCD compared to the screen where you are visualizing it. That's called electronic or digital magnification. So what is happening here is digital magnification if you put a CCD. But when you are viewing with the eye, because we are doing optics, let's learn a bit of what happens when you are viewing with the eye. Well, in case of an eye, linear magnification is irrelevant, or transverse magnification is irrelevant. Why it is irrelevant is, let me just understand why linear magnification is of no use when you are viewing with the eye. I don't know why the same screen is coming back again and again. If you know the answer, you can give me a hint later on. Okay, so, well, what were we discussing? Yeah. So you see, this is the if you consider the eye, now you have the eye lens somewhere here. This is the cornea. This is the eye. The focal length of the eye is about 18 mm. Okay. Now the least distance of distinct vision is 25 millimeter. This is 25 mm. We know this is the least distance for distinct vision. We are asked not to put our reading materials before 25 millimeters. It should be after or at 25 millimeters. Why? Because evolution have ensured that, uh, well, we do not need to see with high resolution within 25 millimeters. Okay. Of course, maybe a crab looking for food underwater may have a least distance of distinct vision of 3 to 4 millimeters. So evolution have ensured that 25 millimeters is just what we need, the distance, minimum distance for distinct vision we need to survive. Okay, so you see the object distance is 25 millimeters. 25, I'm sorry, this is 250 millimeters, not 25 centimeters. So this is 250 millimeters. And the image is formed on the retina, which is about 18 centimeters, 18 millimeters from here. So what is the magnification? The magnification is V by U. So this is your V, this is your U. So it's about 18 by 250. So there is no magnification at all. You cannot expect any magnification with the human eye. It's only minification. The image is diminished. Always. Always. Without an exception. Unless you use a visual aid. So how do we define magnification by the eye when we see a larger object, a smaller object? Well, scientists have said that let us define it in this manner. If the image is formed here, well, it passes the lens, it makes an angle, the extremity of the image makes an angle of theta degrees. Okay, as theta increases, the image size increases, right? So the angle subtended by the extremities of the object on the eye lens is important. Now, because our least distance of distinct vision is 250 millimeters, let us assume that the same microscopic object which we have used there, we have kept here, right? Now, what is the angle that it subtends at the eye? It is, well, if you draw a straight line connecting these points, then this is the angle theta. And we have tan theta. Well, because the angle is very small, the angle is about 1 minute of arc. I mean, to be for the eye to resolve this structure, it is 1 minute of arc. The smallest object, for the smallest object we can put here to resolve between the tip and the base is 1 minute of arc. So tan theta equal to h, if h is the size of the object, by 250. Okay. So because tan theta is approximately equal to theta, so we can write this equal to theta. So remember, theta equal to h by 2. Right. Now, when we are visualizing through a lens, then what happens? This angle should increase. Of course, this angle should increase. Otherwise, you won't have a magnified image. So, in case of a microscope, let us find the angle at which the extremity of the object subtends an angle theta dash, let's say, to the eye, then angular magnification, angular magnification is defined as theta dash by theta, right? This is angular magnification. So remember, eye cannot magnify. Therefore, lateral magnification V by U in case of for the eye is immaterial. So we have to go for angular magnification. And what is angular magnification? Angular magnification is the, well, the angle, it's a ratio basically. On the numerator is the angle which the tip of the object subtends with the aid of a visual instrument, like a microscope. And theta is the angle that it subtends when it is just put at 250 millimeters. Why 250 millimeters? Because before 250 millimeters we cannot see clearly. Beyond 250 millimeters it will be reduced in size. So the maximum magnification we can have is at 250 millimeters. Right. So let us derive the uh, angular magnification of a microscope. So to do that, I need to draw the diagram once again a little bit neatly. Just bear with me. Let's say this is my objective lens and this is my object here. So let's draw two rays from the object. Let's draw with blue. Two rays from the object, one here and then passing through the focus. Let's say the focus is somewhere here and the other passing straight through the center of this. Well, then the intermediate image is formed here. This is the intermediate image. Sorry. It will be, of course, inverted. Okay. This is the tip here, the intermediate image. Okay. And we have the eyepiece. Let's say the eyepiece will put here. This is the eyepiece. So that from the eyepiece, we have a parallel beam coming out, and this parallel beam will be going in the direction of the chief ray, which is this ray. Sorry again. So we have to, let's draw the eyepiece and then draw the chief ray. So now we know that the rays will all be, these rays will be parallel to this. It should have been blue. Okay. And it will, of course, yeah, we have to extend this till it meets the axis. And here you put your eye. Okay. Let's put your eye here. And with respect to the axis, if we extend the axis, then this is the angle theta dash. Okay. Well, right. Now, if this angle is theta dash, then this angle is also theta dash. So if this angle is theta dash, then remember that this distance from the intermediate image to the this lens is Fe. Therefore, you have tan theta dash is approximately equal to theta dash, which is equal to the height of the intermediate image. Let us write it as h prime. So it is h prime by Fe. Okay. Now also, what is h prime? H prime is equal to, well, we have the relation m theta, MMO, that is the magnification of the objective, This is equal to 160, that is the tube length, by FO. So, and we also know that the height of the object H into MO, this must be equal to 160 by FO into H, right? So this is the magnification of the intermediate image. So H prime is simply H into MO, which is 160 by FO into H. So we can write H prime is equal to 160 into H by FO. Okay, and put this here so that your theta prime now comes to H prime, which is 160 into H by FO divided by FE. Okay, so this is your theta prime. What was your theta? Now remember, theta was the angle that the extremity of the same object subtended at the eye, center of the eye, where it was placed at 250 millimeters. So theta is simply H by 250. So what is your angular magnification? Your angular magnification is nothing but uh, m theta. This will be the angular magnification. Is theta prime by theta, which is equal to 160 into h by FO into FE into 250 by h. H cancels out. You're left with 160 by FO into 250 by FE. Well, this 160 by FO, again, bear with me for a minute. Okay, so this is equal to, this we know is 160 is the tube length. So this is the magnification of the objective. And this is defined as the magnification of the eyepiece into ME. So for the eyepiece, if you have a 10x eyepiece, and if someone asks you what is the magnification of this eyepiece, because it's an eyepiece, you have to divide 10 by 250 to get the answer. So the answer will be 25 millimeters, right? So this is the magnification of the objective, 160 by FO. 160 is a tube length, and this is the magnification of the eyepiece. Of course, if you are using an eyepiece, if you're not using an eyepiece, if you're putting a CCD, then it will simply need to multiply with the digital magnification of the CCD, which also depends on the CCD size and the monitor size. Okay, so this is the overall magnification. Right. Now, we need to go into a little bit of, other aspects. For example, the resolution. How does the resolution of a microscope depend? Let me I have to get used to these things actually. Is the writing visible? Can you see the screen? Anyone? Can you respond? Can you see the screen and the scribbling?
Yes, sir, it is visible.
Okay, fine, fine, fine.
Yes, sir. Yes, sir.
Okay, fine, fine. Okay, so we will be discussing diffraction tomorrow, but without a discussion, a brief discussion on diffraction, we cannot complete microscopy. Why? Because you see, let us assume that we have your microscope object is a grating. It's a grating, something like this. Now, what happens? You have a parallel beam of light. Okay. Now, what does a grating have? It has fine structure. It has fine lines. You can have 100 lines per millimeter, 200 lines per millimeter. It is periodic. What about a microscopic object? A microscopic object also have very fine structures, but they may not be periodic. But basically, the same thing happens. And what is that? It is diffraction. So when light falls on a structure which has intensity or phase variations, if it is periodic, then you have these orders passing through. You have the zero order, which passes straight through. You have the first order diffraction, then minus one order diffraction. You have the second order diffraction, minus two order diffraction. Okay, so there are various orders that go out in all directions. Okay, this is for a periodic structure. If it is aperiodic, then it will not have any discrete orders. Light will simply be diffracted in all directions, even if a parallel beam is incident on the structure. Okay, and remember, if you have a coarse grating and a fine grating, what is the difference in diffracted orders? Well, here you have larger diffracted orders. Here you will have smaller diffracted orders. Okay. The same intensity, if you look at the intensity at high, well, and higher order may have the same intensity as a low order here. Of course, both of them will have infinite number of orders, which actually goes on to say that these higher order diffracted beams are actually generated from the fine structures of the object. In other words, if you have to resolve the fine structures of the object, then you have to collect the higher orders. Okay, the higher orders you have to collect. In other words, what we have seen is your MT, the total magnification, is equal to MO into uh, ME, that is the magnification of the objective into the magnification of eyepiece. This is 160 by FO and this is 250 by FE. Okay, so you see that this is the total magnification. Now, what happens if you simply keep on increasing MO? Will the magnification increase? Well, this is where the Abbe's theory, this is a very important theory, Abbe's theory of microscopic image formation comes into play. And it is very easy to understand that suppose you have a microscope objective with only this much, this is my lens, this is my microscope objective, then what will happen? The higher orders will not pass through, your resolution will fall. If the microscope objective becomes larger and larger, if the dimension, physical dimension, irrespective of MO, okay, MO is different, MO is V by U, this is the magnification. But what about the dimension of the microscope objective? As the dimension of the microscope objective keeps on increasing, you are allowing higher and higher orders to take part in the imaging process, imaging phenomenon. That is to say, you are increasing the resolution. And this is where, for a microscope, there is another parameter which is very, very important, which is called numerical aperture. Now, numerical aperture, which is abbreviated as NA, you have this written on microscope objective barrel. Okay, in fact two things are written. One is the magnification, for example 16 25x or whatever, and the other is numerical aperture, maybe 0.25, something like this. This is written on the microscope barrel. Okay, so what is numerical aperture? Well, numerical aperture is, suppose you have an object here. Now before before uh, before that, let me just share one thing with you. Well, I don't know where the drawings have gone. They are vanishing intermittently. But what we have seen is your object distance for a microscope. What is the object distance? Well, if this was the lens, if this was the objective lens, this is FO from here to T. Well, this is T, right? The tube length. And this is FO. The intermediate image is formed here. So, given a particular microscope objective, the image distance is T plus FO. That is always true. That is 160 plus FO. Which is to say, for a 10x objective, what is the object distance? The 10x, for a 10x objective, the object distance is 160 plus, what is FO? FO is 160 by 10, which is 16. That is 176 millimeters. That is to say, given a certain objective, the image distance is fixed. Now, if the image distance is fixed, the object distance must be fixed. Therefore, for a certain objective, the object distance is also fixed. Now, if the object distance is fixed, so given a certain objective, the object distance is fixed. We put the object here. Okay, let us assume we have a point object. So a point object is just a delta function, and you know that if you well, the diffracted orders will be, well, minus infinity to plus infinity in terms of spatial frequency, so it will spread out in all directions. Okay, but only, let's say, if this is my angle theta, the semi acceptance, this is called also called the acceptance angle. Okay, so this is the semi angle of the cone that this point extends on the lens surface, so that these, only these rays can take part in the imaging process. The other rays are, the other diffracted rays are lost. So if this angle is theta and the refractive index of the intervening medium is n, then n sine theta is known as the numerical aperture. I'll take another maximum 10 minutes, okay? So bear with me. So n
Yes,
sine,
sir. Please go ahead.
okay,
Yeah, no problem.
okay. So n sine theta is the numerical aperture of the objective. What does it say? It says that well, as the numerical aperture is greater, if the numerical aperture is greater, then the your microscope objective can accept higher diffracted orders, which means that it will have more resolution, right? Now, that's number one. Also, okay, also, we know that from diffraction theory, from well, Rayleigh criteria. What does Rayleigh criteria say? Well, if you have 2 point objects, okay, suppose you have a point object and you have a lens here. The same thing happens, that from the lens you have the diffracted orders, but not all of them can be accepted by the lens, so some of them goes out. Now, if you want to recreate this point object, you have to capture all the rays that goes out in all directions, but you cannot. Okay, so what happens is here on just a minute. So what happens on the image plane, you do not have a point, but you have a distribution, which we all know is called the Airy pattern. Okay, it's actually a Bessel function. Now, if you have another point object here, you will have another distribution. Okay, something like this. Now, Rayleigh criteria says that we know that if the peak of one image, I mean, this is the image of a point, right? This is one image of a point with a central bright peak, then a dark ring, and so on. This is the other image of a point. If the peak of one coincides with the first minimum of the other, then only you can resolve these two objects as two. Okay, you have a dip in the resultant interference pattern. And we have seen that we already know from diffraction, we'll also discuss this tomorrow, that the separation between the centers of these two in the image plane is given by, this is given by 1.22 lambda f by d. Okay, so on the image plane, the minimum separation between 2 points, which is L minimum, must be equal to 1.22 lambda f by d, right? In case of a, well, microscope objective, in case of a microscope, what is this? Till now, we haven't considered diffraction. We have only considered diffraction when we talked of the numerical aperture. Before that, it was only magnification. But now we know that magnification will not do. If you want to take the resolution of a microscope objective, it is not the magnification that matters. Otherwise, you see, you have, let's say, you have a microscope objective and an eyepiece, ME. Let's say this is 10x, this is 10x. So you get a magnification of 10 into 10, 100 times, right? Let's say this is 100x, this is 10x. Well, you get a magnification of 1000 times. If MO is 10x and ME is 100x, well, mathematics says that you should also get a magnification of 1000 times. But no, you will not get any magnification. Your object will be completely blurred because your objective has only 10x magnification. A 10x magnification is a smaller, 10x objective is a smaller, numerical aperture. But you are trying to visualize larger details because it's a 100x eyepiece. So it's like when you take a photo on a mobile phone and you keep on zooming and zooming and zooming, you will only see a big pixel with no details in it. Okay, and this incidentally is called, well, empty magnification. Empty magnification. So the idea is your objective has to resolve the structures. If it doesn't resolve, the eyepiece cannot help. Your objective will resolve the structures and then the eyepiece will magnify it somewhat. Okay? Okay. So L minimum is 1.22 lambda f by d, and we have seen that the numerical aperture is defined as, if this is your lens, this is actually, well, what is d? Let me draw the parameters. Lambda is the wavelength of light, f is the focal length of the lens, and d is the diameter of the aperture of the imaging lens. Okay, this is d, right? So we can write this as is equal to 1.22 lambda, uh, 2 into d by 2 f. Okay, now d by 2 is the radius. This is the radius. This is the radius. Okay, and f is this distance. Well, it is, remember, we'll take the object distance to be f because in most microscopes, for most microscope objectives, the object distance is very, very close to f. It is very close to f. In fact, for a 40x objective, it is, let's say, f plus minus point some millimeters. Okay, for a 100x objective, it is even less. So if you take this to be f, then d by 2f, we can approximate this to be, well, sine theta, and of course the n, the numerical aperture will come in. So this becomes 0.61, 0.61. So the minimum resolvable distance for a microscope objective is equal to 0.61 lambda by numerical aperture. Okay, this is the next important equation we have for a microscope, which means the resolving power. What does L minimum mean? It means the minimum distance between 2 points. So if this is one point, this is the other point. The minimum distance between 2 points that the microscope can resolve, this is zero point 0.1 lambda by numerical aperture. Right. So what is the resolving power? The resolving power is equal to numerical aperture by 0.61 lambda. This will be lines per lines per millimeter. Okay, so the resolving power is given by numerical aperture by 0.61 lambda lines per millimeter. So for a 10x objective, given a 10x objective, m theta, mo, let's say, the numerical aperture is standard for 10x objective 0.25. And suppose we have, well, lambda, let us take to be 500 nanometers. Then what is the resolving power? The resolving power we know would be 0.25 divided by 0.61 into 500. Now this is lines per, numerical aperture. Lambda is given by nanometers. So this will come out to be lines per nanometers. So you have to multiply this with, well, 10 to the power 6 to have lines per nanometer. 10 to the power 3 would be lines per millimeter, micrometer, and then 10 to the power 3 again, right? So this we can say would be the resolution of a, well, microscope objective, 10x microscope objective. Now naturally a 100x microscope objective will have more resolution, will have more magnification, therefore it needs to have more resolution. Okay, and strangely, the, for a 100x objective it is greater than 1. Now you might ask me, why is greater than 1? It can have 1.2 also. Why it is greater than 1? Because it is sine theta. Sine theta cannot be greater than 1. But you're forgetting that there is a n sine theta factor here. This n factor is here. Okay, so what happens is, in case of a 100x objective, we use an oil between the objective and the slide. So you have the slide here, you put a drop of oil on the cover slip under which the sample rests. Okay, now as you bring down the microscope objective, because remember, for a 100x objective, the object distance is very small, a fraction of a millimeter. So as you bring it down, this oil spreads out because of surface tension, and it forms a medium between the object and the lens. Okay, thereby what happens is the diffracted light, which otherwise, this is my incident light, illuminating beam, the diffracted light which otherwise would have escaped the lens now is diverted towards the lens. Okay, so as you increase the magnification of the objective, you have to increase the numerical aperture of the objective also. Otherwise, you want to have increased magnification for higher magnification objectives. So in other words, you need to have increased resolution also. Okay, for higher spatial frequency. Spatial frequency, incidentally, is, well, hertz. Temporal frequency is hertz, right? What is hertz? Number of oscillations. Number of oscillations per second. This is temporal frequency. Temporal frequency. Spatial frequency is number of oscillations in space, which means per unit length. Okay, for example, if you have a grating, then Well, this is number of oscillations. If you go across this, it will be something like this, right? So number of if it's a sinusoidal grating, then it can be something like this. So it is in space, it is in one direction, x or y. So it is number of oscillations per unit length. This is called spatial frequency. So greater is the well, the numerical aperture, it can resolve higher spatial frequencies. For example, 10x objective can at best resolve, let's say, 100 lines per mm, whereas a 100x objective would be able to resolve 1000 lines per millimeter. Okay, so for a microscope object, it can resolve finer structures which are as small as about 1 micron. I think I should end here. Okay, so let's stop sharing.
Yes.
Yeah.
Uh, Participants, if you have any questions, please share in the chat. Sir will be available. Otherwise, you can note down the questions and then we can take it in the next class. Tomorrow, sir will be there as well. He will be sharing the remaining two topics that are there under quantum optics.
How many participants are there right now?
Sir, 1 minute. So there are 332 now.
Okay, okay, okay. So
There
this
were
is
about.
just, is this just a one-way communication, or should I get some?
No, sir. Actually, yeah, some questions are there, sir. Maybe you can open you if you can click on the chat option.
Okay, okay.
I'll read out some questions. Not many questions actually.
Uh-huh.
Uh,
Chat
where
option
can
is,
we?
yeah, yeah.
Yeah.
Show chat,
Yes.
but please suggest books on optometry and optical instruments. I can see this question, Mankala Rajeshwara. Okay, where do I have?
Yes, sir.
Well, optometry is a different subject. Optometry is related to the eye. Okay, optical instruments you can well, Hecht, Optics by Hecht is a good book. Okay, you can also have Optics by Hecht, and Professor Ajay Ghatak's book is also, you can have it with you. So these are basic standard books on optical instruments. Optometry is a different subject altogether. Okay, it concerns the eye, the aberrations of the eye, the focal length, and all those things. So that's we are not dealing with that. There are dedicated books on optometry. Yeah, what else?
Where can we use optics in quantum computing is another question. Dr. Kupuswamy.
In quantum optics? Well, in see, whatever we have done here, we have treated light as waves, okay, electromagnetic waves. Now, instead of electromagnetic waves, if you treat light as photons, as particles, the whole field of which goes into quantum optics, because light then will be described in terms of quanta. Okay, and because light, a photon has no polarization, so it will be thought of as a superposition of two polarized states, right? So it will be a superposition of two polarized states. In other words, polarization is very closely linked to spin. So you say upspin and downspin, right? I think you will cover these more in your quantum uh, optics class. Anything else?
Yes, sir. I think, yeah. Any participants, if there are any questions, please.
I
I
hope
think,
there was a problem with the whiteboard. I have tried to correct it next time.
right, sir.
Otherwise, I don't know if you enjoyed it. Okay. Uh,
And they enjoy it, sir. Actually, there are 2, 3 faculty who use the whiteboard or blackboard. In fact, one sir uses a black screen with a white chalk, white,
yeah, I
writing.
also used to do that, but this
Right,
is a
right.
new
So,
one
so
that I have downloaded yesterday. So Because we were using this during the COVID times.
Right,
So
sir.
after a
Yes, sir.
very long time, I brought it out and tried to
Correct.
refigure this. Okay. Anyway.
Yeah, that part is no problem, sir. And actually, the basic idea is some of the topics, some of the physics faculty are also there.
Mm.
Some computer science faculty are there. Some people may be aware of that. Many are PhD holders, sir. Actually, it's a very good faculty who are participating, very serious and very
Okay.
keen on this. So that way, some people may be aware. Some people must have really enjoyed. No questions means well understood. So that's what I would say.
Or nothing
So,
understood, whatever.
yeah,
Anyway, I think this was
right.
very basic to those who are in optics. I mean,
Yeah,
these are
yeah,
very
yes, sir.
basic
Yes.
things. Okay.
Actually, the course content has been assigned so that engineering students understand it. So what we are doing is we are trying to train the faculty who will handle these courses in the later point.
Understand.
And most of them are from interdisciplinary background. So that's where we're trying to bring them all at one level. So some
Understand.
people will have an advantage and some people will, try to understand how these things will go. Yes, sir.
Okay.
Uh, yeah,
Okay.
quantum optics circuits will also be discussed. I think quantum optics is coming in QT-11. We are in 5. QT-11 is totally dedicated to quantum optics, and I think we'll have Bhattacharya sir again coming back at that time also. We'll try to request some things. Yeah, we can
Yeah,
try to
the
do that.
concept of, I think I'm getting some messages. Qubit, the concept of qubit as a superposition of polation states and all that. You will do that later. But today is only optics, okay? We're not going to quantum.
Right, right.
Right.
Yeah, Rajeshwari madam, maybe tomorrow we can do it. I think because we start with quantum optics, will take some time for her to articulate and present it as well. So today we'll stick to optics. Whatever sir has start, if you have any questions, we will have that because anyway time is also extended today. Tomorrow we'll start sharply at 3 and then we will have enough time to for the question answers, right? And maybe in between. Sir, maybe tomorrow around
Mm,
3 o'clock, 3
mm,
to 4, you can take the lecture. Around
mm.
4 o'clock, you can give a break for some time so
Okay.
that they will actually articulate some questions and put it. Then you can also take a break kind of. And then again, we'll start after that and complete at 5, take few questions and conclude. Yeah.
Okay.
Thank you
Fine.
so much,
Fine.
sir, for
Fine.
your valuable time. Uh,
Thank
Thank
you.
you for
Thank you.
being with us. And thank you, participants. We'll meet at 3 o'clock tomorrow. Sir will continue with the lecture on optics. Right. Thank you.
Okay then.
Thank you, sir.
I'm taking a leave now then. Huh?
Yes, sir. Thank you, sir.
Okay. Thank you
Thank
so
you, sir.
much. Thank you.